We know humans impact the Earth, so what do we do about it? We design solutions. A design solution is any technology or method created to solve a problem, like making a car that uses less gas or a way to clean up ocean pollution. Our job as scientists isn't just to invent these solutions, but to critically evaluate them. We need to use strong evidence to figure out which solutions work best and which ones might actually cause new problems. When evaluating any solution, we look at two things: the criteria and the constraints. The criteria are the goals. What does the solution need to achieve? Does it need to save water? Does it need to be cheap? The constraints are the limitations, the things that stop the solution from being perfect. This includes the budget, the materials we can use, and importantly, the requirement that the solution itself shouldn't cause too much new environmental harm. One popular design solution for the atmosphere is using solar panels. The goal is to reduce the carbon dioxide released from burning coal. The criteria for success are that the panels must generate enough reliable electricity to power a home or city, and they must save money over the long haul. The main constraint is the high cost to buy and install them initially, which puts them out of reach for some families. How does this solution evaluate? Positively, solar panels create zero pollution when they are running. They are a clean source of energy. Negatively, the manufacturing process is complicated. Making the panels requires mining rare minerals from the Earth's geosphere and a lot of energy, creating a secondary environmental impact. We must weigh the long-term clean energy benefit against the short-term mining cost. Let's evaluate a water solution: low-flow fixtures. These are specialized shower heads and toilets designed to reduce the amount of water used in a bathroom. The goal is to reduce water scarcity and the overuse of the hydrosphere. The main criteria are that they must save water while still being effective for washing and flushing. A common constraint is that these fixtures sometimes cost more than traditional ones when you buy them at the store. The evaluation of water-saving fixtures is generally very positive. They dramatically reduce the daily water consumption for a family without requiring a major change in lifestyle. This helps keep more water in rivers and underground aquifers. The negative impacts are mostly social. Some people complain that a low-flow shower doesn't feel powerful enough, which can sometimes be a social constraint that prevents people from adopting the solution. For cities, a solution to traffic and air pollution is mass transit, like electric buses or trains. The goal is to reduce the number of individual cars on the road. The criteria are clear: move many people efficiently, safely, and on time. But the constraints are huge. Building a new train line or subway system costs billions of dollars and requires massive construction that disrupts the geosphere and biosphere where it is built. Positively, mass transit is great because one bus can take dozens of cars off the road, saving a huge amount of gasoline and cutting down on smog. Negatively, that initial infrastructure construction, the tracks, the stations, the power lines, can destroy natural habitats or displace communities. This is a classic trade-off. We're solving a pollution problem, but creating a temporary habitat destruction problem. What about dealing with trash? Waste to energy, WTE, plants are a design solution. The goal is to solve two problems at once: reduce the volume of trash in landfills and create useful energy. The criteria is that they must safely incinerate the garbage while producing electricity. A major constraint is that building these large, complex plants is technically challenging and very expensive. The positive evaluation for WTE is powerful. It can shrink the volume of trash that goes into the geosphere, landfills, by up to 90%, and it produces electricity that goes back into the grid. However, the negative trade-off is that burning trash creates smoke. If the plant's filtration system isn't perfectly maintained and highly advanced, it can release harmful gases into the atmosphere, causing local air pollution. To reduce the enormous land footprint of agriculture, engineers developed vertical farms. The goal is to save massive amounts of land and protect the biosphere. The criteria is high-yield food production year-round in an urban setting. A huge constraint is the energy demand. These farms rely on powerful electric lights for all of the plant's photosynthesis needs, which requires a constant, large supply of electricity. Vertical farms score big positive points for the environment. They use less than 5% of the water of traditional farms, require no pesticides, and completely protect the habitats that were not cleared for farming. The negative trade-off is their reliance on energy. If the local electricity comes from a coal-burning power plant, the vertical farm is actually indirectly causing significant air pollution and CO2 emissions. The most common constraint that stops a brilliant design solution is cost. A design solution must be financially sustainable. We have to ask, is this only something wealthy countries or rich people can afford? If a perfect water cleaning system costs $1 million, most small towns can't afford it, and the pollution problem continues. When evaluating, we must find the most effective solution that fits the budget, the economic constraint. You've heard this a few times now. Almost every solution involves an environmental trade-off. We are constantly trying to choose the least harmful path. Electric cars are a great example. They eliminate tailpipe emissions, solving a local air pollution problem. But to make their batteries, we must mine lithium and cobalt from the earth, which damages the geosphere and local environments. Our evaluation is about choosing the solution where the overall benefit to the earth systems is the greatest. How do we know if a solution works? We need data as evidence. You can't just think a low-flow toilet saves water. You need to track the community's water meter readings for a year, before and after the installation. If the data shows a 25% drop in usage, you have the proof. The solution is effective. Scientific evaluation requires quantifiable evidence, not just good intentions. Sometimes the best solution is stocked not by money or materials, but by people. This is the social constraint. People need to be willing to change their habits. If a city builds an amazing, clean train system, but people still prefer the convenience of driving their own cars, the solution fails to meet its criterion of reducing traffic. A design solution must be practical and convenient enough for society to adopt it. The role of engineering is continuous improvement. When we identify a negative trade-off, engineers are tasked with solving that new problem. For example, we know that electric car batteries are hard to recycle, a negative trade-off. So, engineers are now developing new designs for batteries that use more common materials, or developing new chemical processes that make the recycling of the old batteries easier and cheaper. When evaluating a solution, we must look at its longevity. Is it a quick fix or a permanent solution? Turning off lights saves energy for 1 hour, short term. But designing and building a massive, clean power facility, like a solar farm, is a solution that could provide clean energy for 40 years or more, long term. The best solutions are those that solve the problem for the longest time possible. There is no one-size-fits-all solution. The best option depends on the local context. A coastal city with access to unlimited ocean water might find a desalination plant to be a great investment despite the high cost. However, a town in a landlocked, windy plain would be better off investing in wind turbines for clean energy, as they would be more effective than solar panels in that specific environment. Our final job is to remember that designing for sustainability is a process of constant evaluation. We must use our criteria and constraints to carefully weigh the pros and cons of every solution. By continuously applying scientific principles, using evidence, and designing cleverly, we can meet the growing needs of the human population while engineering a future that is in harmony with the health of all Earth systems.